Okay, hello all you crazy people out there. My name is Michael, I like wizards and dragons and making games, and let's talk about making games. So far, when we've talked about color in computers, we have talked about color in terms of red, green, and blue components, and we have been able to get pretty far with that. The red, green, blue system works pretty well. The reason we have the system in the first place is because the red, green, and blue color components map pretty nicely to the red, green, and blue light-emitting diodes that compose each pixel in your LED monitors and computer screens. And they can each shine with varying levels of intensity between fully on and fully off. From there, the three types of cone cells in our human eyes can detect the different wavelengths of light that these LEDs emit. And assuming you have normal color vision, our brains turn this into all the colors of the rainbow.
Hey.
And all that is to say that the red, green, blue color model is pretty close to how our human brains physically interpret light and the way that our eyes physically detect color. But at least for most people, red, green, and blue isn't very similar at all to how people really intuitively understand color. My dog just walked in the room. You do not have full color vision. How exactly does dog vision work anyway? I want to say they can only see like blues and yellows. Anyway, the way that most people would intuitively understand color would be by looking at something or imagining something like a spectrum or a rainbow, where you have red on one side and violet on the other, or perhaps something like a color wheel, which has, for example, red on one side and its complementary color green on the other, or blue on one side and its complementary color orange on the other. And for that reason, if you were to open up an image editing tool such as Adobe Photoshop, or maybe an artist tool such as Krita or something like that, and if you were to bring up a color selector, you would in fact see, most of the time, in a lot of cases by default, instead of red, green, and blue, you would see something like hue, saturation, and value, where you have a hue shift, so all the colors of the rainbow on one axis, and perhaps you have the amount of color, the saturation on another axis, like you can see here. Fully saturated in this case being 100% red, and unsaturated being 100% white, and value on the third axis, with the brightness of the color. So a brightness of 0 gives you black, a brightness of 1 gives you either white or fully saturated red or something in between. And you can use this model of colors to modify the way that an image looks. For example, you could shift the hue of the of this here Frogger sprite, and you could change it from red to something maybe greenish or bluish, or in the other direction, very dark red, purplish. And you can change the saturation, which is the amount of color. Again, you could make it a very bright, a very loud red, green, and yellow sort of color, or you could reduce it the other way and you could turn it into basically grayscale. On the lightness front, on the brightness front, you could increase the brightness to wash it out to make it look very white, or you could decrease the brightness to darken it to make it black, to fade it to black. And you might wonder if it's possible to do something like this in a shader, in computer graphics, in code, and the answer, as you can imagine, is yes, as is the answer to many of these sorts of questions. I have here in this demo program, I have some saturation and value color adjustments, so I can bring the saturation all the way up to make the Frogger sprite very bright red and blue and yellow. I could bring it all the way down, and we will have effectively a grayscale image. It's not quite grayscale in this case, but it's pretty close. I can reduce the lightness, or the value, and I could turn it black. I could increase the lightness, and I could turn it white. I'm actually going to talk about hue shifting another day. That's a whole subject of its own. So that's my demo program. In my actual GameMaker project, I have some of that code written, but I don't have the actual color modification implemented yet. We will be doing that in this video. So you can see if you hit the arrow keys on the keyboard, you can change the numbers that for the saturation and value values, but we will not actually be changing anything in the image. So in this demo project, we are first drawing the unmodified version of the sprite so that we can have sort of a control so that we can compare the final result against. And then we are setting the shader. We are setting the saturation and brightness shader, as I have titled it, which again is just basically, it doesn't do anything yet. We'll be getting to that shortly. And it sets the saturation and value uniforms, and then it draws the modified version of the sprite. So there's nothing in the Vertex Shader, or at least nothing of interest. This is just a pass-through Vertex Shader. The Fragment Shader's got a little bit of stuff in it. Firstly, we are just fetching the actual color of the sprite texture, multiplied by the vertex color, as you would ordinarily do. And then we are modifying the red, green, and blue components of the fragment shader output using this adjust saturation and value function. And the adjust saturation and value function just returns a vector 3. It takes a vector 3 as an input, and it converts the source color in the form of red, green, and blue to HSV, to hue, saturation, and value, and then it converts it back. And in the middle, this is where we're going to modify our color. So 2 functions, 2 HSV and 2 RGB. This is going to be the meat and potatoes of this video. We are going to be converting a color value from red, green, and blue to hue, saturation, and value, and then back. Let's start with converting from red, green, and blue to HSV. So you may have seen at some point what some code looks like to convert between a red, green, and blue color to hue, saturation, and value. If you have, it probably looks something like this. It's a little bit long. It's got a lot of if statements, and it's got a lot of different conditions to essentially separate the different red, green, and blue color values into the different sections of the color wheel. You can convert that to shader code if you want, and it will work. It's got a lot of ifs and if-elses and that sort of thing in it, but it shouldn't perform too badly at the end of the day. But it is a lot to type out, so fortunately there are other ways to convert between red, green, and blue and hue, saturation, and value. And the version that I'm going to write here is a little bit friendlier to run in the form of a shader because it's, well, simply put, it's not going to have nearly as many if statements in it. I'm doing this in GLSL, by the way. If you want to do this in HLSL or some other shader language, it should be fairly easy to adapt this shader code to your shader language of choice. So let's start by defining a vector 4. I'm going to call this k. And this is going to be a vector 4 composed of, let's see, 0.0 on the x. I'm going to space these out a little bit. Negative 1.0 divided by 3.0 on the y. 2.0 divided by 3.0 on the z. And on the w, negative 1.0. So that's going to be 0, negative 1/3, 2/3, positive 2/3, I mean, and negative 1. And let me pause for a moment to just bring up a point about vectors, and that is that when you have something like a vector 4, you could access its components as either the vector.rgba for the red, green, blue, or alpha, or you could access the components via something like x, y, z, and w. And these two are equivalent. R and x are always going to be the first component of the vector, g and y are always going to be the second components of the vector. B and Z are always going to be the third components of the vector, and A and W are always going to be the fourth components of the vector. It doesn't matter what you use. It doesn't matter if you use R or X or anything like that. R and X will both access the same values. What you would generally do is the variable names that you would use, the letters that you would use to access each of the components of a vector would depend on the context. So if you're dealing with colors, you would probably use R, G, B, and A, and if you're using positions in space, you would probably use X, Y, Z, and W. And this goes for vectors of other sizes as well, not just vector 4s. So with that said, to hopefully head off some confusion, some potential confusion, I will leave comments, and I will just leave a little note about the components that I will be using to access each of these values when I declare them. So the color, the input color, as you can imagine, is going to be red, green, and blue as a vector 3, and K here. You could use red, green, blue, and alpha for this as well as a vector 4, but just to hopefully make things a little bit less confusing, and to hopefully reduce the chances that either I or someone who's watching this will mix up the different vectors that we're using, use instead X, Y, Z, and W for K instead of red, green, blue, and alpha. And I will attempt to remember to do that with every vector that I define in these two conversion scripts here, in these two conversion functions. So I'm going to define a few more vector 4s, and the first one I'm going to do is going to be named the letter P. P, thank you. And vector 4P is going to be the result of the mix function. The mix function, I mentioned it a couple times in the past. It is essentially GLSL's version of lerp, linear interpolation, as you might see it in GameMaker or in some other math libraries and other computer languages. The mix function will take two values, a start and an endpoint, and it will return a result which is somewhere in between them based on some transition amount. If your start and endpoints into the mix function are 0 and 10, and your transition amount is 0, your third parameter is 0, then the mix function will return 0. If the transition is set to 1, it will return 10. If it's 0.5, it'll return halfway between 0 and 10, so in our case 5. If the transition amount that you give it lies outside the range of 0 to 1, it will extrapolate the values instead of interpolating them, but that's not something that we're going to really have to worry about here. And the mix function is also a generic function. It can take a vector of any size, a vector 2, a vector 3, a vector 4, whatever. It can also take floats. I think it works on matrices also.
Hey.
And if you give it a vector type as its first two parameters, it will perform the operation component-wise and return a vector of that same size, with each of the components being interpolated separately. It's a very handy function. You tend to see it a lot in shaders. So I'm going to pass the mix function a vector 4, and the vector 4 is going to contain a bit of a hodgepodge of different values between the input color and the k value here. Firstly, we're going to be saying color.blue. Secondly, color.green. Thirdly, k.w. And fourthly, k.z. And you can combine these a little bit to make this a little bit less code and to make it look a little bit better. You can say instead of color.b and color.g separately, you can combine them like this. You can say color.bg. But for the sake of clarity, I think I will choose not to do that right here. The second value that we're going to pass into the mix function is going to be a vector 4. This is going to contain components of color.g, color.b, k.x, and k.y. So just to go over this again, color.b, color.g, k.w, k.z. In the first one, that sort of rhymes. In the second one, color.g, color.b, k.x, and k.y. Okay, that looks correct. And the third value needs to be a float. This cannot be a vector. Ideally, this is between 0 and 1, as I said earlier, although mathematically it doesn't have to be. We are going to be using a value of 0 if color.green is less than color.blue, and a value of 1 otherwise. And that sounds suspiciously like an if statement. And I suppose if you wanted to, you could use an if statement for this. You could say if color.g is less than color.b, and you could perform some operation. But there's a handy function which is built into the shader language called step, which will more or less do this for us. This is technically hiding an if statement. Technically, under the hood, we're still doing a branch in a shader, which I know is scary for some people, but it's a branch which the graphics hardware is a little bit more optimized to do.
Hey.
At least compared to the big, ugly if-else tree that is the alternative HSV color conversion. And we are going to pass this two parameters, color.b first and color.g second. And the step function is going to take two input parameters, and it is going to compare them, and if the second parameter, so in our case color.g, is less than the first parameter, then it's going to return 0. Otherwise, it's going to return 1. And that's going to be vector 4p. Next, let's define another vector 4. Let's call it q. So we have p and q as our two vectors. And this is going to look somewhat similar. We're going to be using the mix function again. We're going to define another vector 4. The components of this are going to be p.x, p.y, p.w, and color.r. So p.x, p.y, p.w, and color.r. We're going to be making use of the first vector 4 that we defined up here. The second vector 4 is going to be vec4 color.r, p.y, p.z, p.x. Did I get those? Color.r, p.y, p.z, p.x. That's what my notes look like. That should be correct. And we are going to be giving a step of p.x and color.r. So if color.r is less than p.x, it's going to return 0. Otherwise, it's going to return 1. Okay, those are the vectors that we need, at least to set up. Let me go down a few lines and define a float. I'm going to call this d. This is going to be equal to q.x minus the minimum of q.w. Next, I'm going to say float e is going to be just an arbitrarily small number. I'm going to say 0.0001. The actual value here isn't terribly important. This is just going to be here so that we, as a minimum value, so that we don't accidentally divide by 0, as we're going to see in a minute. And lastly, we're going to return a vector 3. And this vector 3 is going to consist of a few values. The first is going to be the absolute ABS, the absolute value of q.z plus q.w minus q.y, divided by 6.0 times d plus e. Again, e is here so that we don't accidentally divide by 0. In this term, if d happens to be equal to 0, if this calculation happens to be equal to 0, then we would divide by that value, and that could lead to unpredictable results. That could lead to undefined behavior. So we're just going to add this small value here as an extra term just to make sure that that doesn't happen. Let's see, I need another closed parentheses there, and that will round off the absolute value function. The second component of this vector 3 is going to be d divided by q.x plus e. Slightly simpler, no absolute value function here. And again, you're going to add the e, you're going to add the little epsilon term just in case q.x happens to be equal to 0, so that you don't have a division by 0 on your hands. And the third value is the simplest of them all. This is just going to be q.x. Close parentheses on the vector 3 constructor, followed by a semicolon. So this 2HSV function is going to return a vector 3, and it's going to contain the components, instead of representing red, green, and blue, it's going to contain components representing instead hue, saturation, and value. And they are all going to be between 0 and 1, rather than, for example, 0 and 360 degrees, as you often see in, as you might often see hue represented in something like an image editing tool. If I were to run the game now, it would look interesting. I'm actually not 100% sure what it would look like exactly. It's definitely not going to be red, green, and blue. And you can see that we have done some really funny, strange effect to this frog sprite, with the outline being green instead of black, and the body being like blue instead of red and yellow. And I suppose, since I did say I was going to label these, we are returning a vector representing HSV, and I'm going to be using the components x, y, and z for this. Mostly because it would be very confusing if I had a vector 3 representing hue, saturation, and value, and I would attempt to access its components by saying red, green, and blue. That would be extremely confusing. So next, we would like to be able to undo this. Once we have the HSV color vector, we would like to be able to turn that back to red, green, and blue for future use. And undoing this function, the inverse of this function, is a little bit nicer than doing the operation the first time up here. It's going to be a few fewer lines of code. First, let me just make a note. The input color is going to be HSV, and I'm going to be using the components x, y, and z to access it, to access the things inside them. Firstly, let me define vector 4k. This is going to look similar to vector 4k up in the 2HSV function. It is going to, instead of being 0, negative 1/3, positive 2/3, and negative 1, we are going to be looking at 1.0, positive 1.0, positive 2.0 divided by 3.0, so positive 2/3, and then positive 1/3, so 1.0 divided by 3.0, followed by 3.0. And you could like write these out for yourself if you want. You could say 0.66666 for 2/3. You could say 0.33333 like this for 1/3. I'm just going to go with the fractional representations, just so that that's more exact. And k is again going to be x, y, z, and w instead of red, green, and blue. Next, vec3 p is going to be equal to a vector 3 containing the absolute value of, I'm going to be using the fract function here. The fract function returns the fractional part of a number, past something like 5.2 as an input parameter to it. It will return 0.2, it'll return the fractional part. And likewise, just like the mix function, both the fract function and the absolute value function will return, will take a generic type, and it will return the value component-wise if you give it a vector. So if you have a vector that goes into the fract function, it will return a vector of the same size with the fractional parts of each of the components. So what's going to go into this fract function is going to be a vector 3, and this vector 3 is going to be composed of color.x minus plus k.x, followed by color.x plus k.y, followed by color.x plus k.z. Close the vector constructor, close the fract function, so 2 parentheses there. And we're going to multiply this by 6.0. And then we are going to subtract a vector 3, which is composed of k.w, k.w, and k.w. Alright, parentheses are all matched up. That looks like the parentheses are in the right place. You could shorten this a little bit. You could, instead of going through all these vector constructors, you could use the aforementioned, like, swizzled values. Yes, that's what it's really called. And say something like color.xxx plus k.xyz. But, again, for the sake of readability, I'm going to choose to not do that, and I'm going to write this out the long way. If you enjoy using vector components like that, you are perfectly free to do that. I'm just not going to. And this is going to return a vector 3. I'm going to label this, and I'm just going to say P is going to be XYZ. And I realize I actually forgot to label these two up here. I believe these are both XYZ. XYZW. For the sake of completion. Next, to finish off the 2RGB function, we are going to return a value, and that is going to be a vector 3. And this vector 3 is going to be the result of the mix function, which is going to take a vector 3 in the form of k.w, k.w, and k.w.
Hey.
The second vector 3 that goes into this mix function is going to be the result of the clamp function. Clamp is essentially doing min and max at the same time, so it's going to constrain a value between two other values. And what we are going to be constraining is going to be the vector p that we defined up here, minus a vector 3 composed of k.x, k.x, and k.x. And again, you could combine these into a single expression if you want. You could say p minus k.xxx instead of going through the vector 3 constructor, but I am not going to do that. And the values that we are going to be clamping this expression between are going to be a vector 3 of 0, 0, and 0, and a vector 3 of 1, 1, and 1. And that is going to be it for the clamp function, and the amount of, the interpolation amount, as I've been calling it, is going to be color.y. And we're going to take that, we're going to close parentheses, close the mix function, multiply by color.z, and that's going to be that. I suppose just because I'm doing it everywhere else, 0.0 for the vector 3 constructor, and 1.0 for the vector 3 constructor. The shader compiler will do this implicitly when you pass an integer into a vector constructor like this, but again, readability. So I unfortunately don't have a great way of describing exactly what each of these steps are doing visually when it comes to converting a value from red, green, and blue to HSV, but you can sort of make out in here in this when you're going back to RGB. Color.z, so the third component of the input HSV vector, is the brightness, with 0 being black and 1 being fully bright, 1 being fully white. And you can imagine the result of this this initial value being multiplied by that brightness, some value between 0 and 1, that would have a bit of a darkening effect on the final color, based on the brightness value. So now, if I were to run the game, let me just do this, and we are going to see it is not correct. All right, what happened? Okay, I see what I did. This first one needs to be k.x, k.x, and k.x. So the first vector 3 in the mix function in the 2RGB function needs to be the x component of the k value. And now we're going back to normal. Okay. Small mistake. I'll probably have thrown text on the screen pointing that out when I first wrote that. Okay. So we have gone successfully from hue, saturation, and value to red, green, and blue. Now we probably want to do something with that value. So the promise that I made at the beginning, in that we are going to be using the uniform saturation and uniform values to modify the color, to modify the saturation and value of the Frogger sprite. So these are going to range between 0 and 1. They're going to go up and down when you hit the different arrow keys. I am going to perform the simple operation of HSV dot, and I suppose I will denote the components that I'm going to be using for these values as well. Color is going to be red, green, blue. HSV, it's going to be X, Y, and Z. So let's start with the saturation. I'm going to say HSV.Y is going to be equal to the maximum value of 0.0, so saturation can never be negative. And HSV.Y plus saturation, uniform sat, uniform underscore sat. And that will allow us to mess with the saturation. Let's see, if I were to go up, we're going to be having the color become much more intense. If I were to go down, we would have the saturation go down, and we're going to have a grayscale. Okay, value, also known as sort of, value and brightness aren't quite the same thing, but they're pretty similar, and I'm pretty sure that I've been using them interchangeably throughout this video. Anyway, value does not yet do anything. We can mess with that in a moment. Value is going to be very similar. I'm going to say HSV.Z equals max of 0.0 HSV.Z plus uniform val. And that will allow us to modify the value. So we now have ourselves a shader, which allows us to play with the saturation and value of our frog sprite. I believe you might want to also constrain HSV.Y and HSV.Z, so the saturation and value at a +1, as well as not allowing them to go negative, but I don't think there's any, like, negative effects of, You can do that if you want. I'll be leaving this as it is. If I bring the saturation and value all the way up, you can see it looks very... I almost want to call this, like, cookie cutter-like. The contrast is almost entirely gone. The entire frog's body is just bright red. If I were to bring the value down, or the saturation down, we would have basically a black mask. If I were to bring the saturation down and bring the value all the way up, we would have essentially a white mask. So that's saturation and value. So, I have not made any commits in this entire video, so I'm just going to be committing this entire mess of code as one. Saturation and value shader. Like I said at the beginning, you can do hue shift in a similar way. You can do hue shift by converting a color to HSV and then modifying the hue value, but there are other ways of doing hue shift, and they do produce slightly different results, one of which I think looks a little bit better. And that is going to be the subject of the next video, at least the next video that I do on shaders, which will be either next week or the week after, depending on if I'm able to finish what I want to work on for next week by then. So that is it for me for today. If you would like to see the code for this, look in the video description for the GitHub repository. Otherwise, I try to post about 2 game dev videos a week, one of these and one Let's Make a Tower Defense game. So if you're interested in seeing any of that, or just a whole bunch of Let's Plays, feel free to subscribe. I have a Patreon, so if you want to contribute towards these videos being made, there will be links to that in all the usual places. Otherwise, I hope you found this useful, and I will see you all later. Special thanks to Connor, David Key, Edward Holt, Emily Koyo, Halo Factory, Posho, Syndra Larson, Tusk, and Zenith for supporting these videos. If you want to see your name in the credits or to hear yourself shouted out at the end, head on over to the Patreon page down in the video description to join the fun.